AI's energy boom is stressing the grid. Where does hydrogen fit? AI is no longer just a software revolution, it is becoming an energy event. The expansion of data centers, model training clusters, inference workloads, and industrial AI integration is translating directly into electricity demand. And not incremental demand, structural demand. Regions that once saw steady, predictable load growth are now facing concentrated, high-density 24/7 electricity consumption from hyperscale data centers. The grid was not designed for this kind of acceleration. The real question is not whether AI will scale. It is whether power systems can scale at the same speed. And when they cannot, what fills the gap? Let's start with what is verifiably true. Data centers are expanding rapidly. AI training models require enormous compute intensity. Inference is becoming constant rather than periodic. Cloud providers are building larger campuses, often requesting hundreds of megawatts per site. In some grid territories, data center interconnection requests represent a significant portion of future load growth projections. This is not speculation. It is appearing in utility filings, grid operator outlooks, and infrastructure investment plans. However, it is important to remain precise. Not every grid is on the brink of collapse. The stress is regional. It depends on transmission constraints, generation mix, regulatory timelines, and capital access. But in constrained corridors, particularly where renewable penetration is already high and transmission expansion lags, the tension is visible. Transmission build-out takes time. Permitting high-voltage lines can stretch for years. Substation upgrades are not instantaneous. Meanwhile, hyperscalers operate on shorter timeframes. They secure land, sign procurement contracts, and expect electricity delivery aligned with digital infrastructure build cycles. When those cycles mismatch, bottlenecks appear. Now we layer in renewable variability. Solar output peaks midday. Wind varies seasonally and hourly. Batteries help manage short-duration fluctuations, but they do not provide multi-day or seasonal balancing at grid scale in most current deployments. Gas turbines remain the most common dispatchable solution, but they introduce carbon exposure and fuel price volatility. Nuclear offers firm power but requires long development timelines in most Western jurisdictions. Pumped hydro is effective but geographically limited. Compressed air and flow batteries are emerging but not yet deployed at scale in most markets. This is where hydrogen enters the conversation. Not as a silver bullet, but as one of the few technologies capable of storing large amounts of energy over extended durations and reconverting it to power when needed. Hydrogen can be produced when electricity supply exceeds demand, stored in tanks or underground caverns, and used later in turbines or fuel cells to generate electricity. The round-trip efficiency is lower than batteries. The capital cost is higher than gas. But efficiency is not the only metric under system stress. Duration and scale matter. The key shift in this AI-driven energy era is the value of firm, reliable power. AI workloads do not tolerate downtime easily. Data centers are engineered for redundancy. If electricity systems struggle to provide consistent clean power, operators will seek layered resilience strategies. That may include grid supply, on-site renewables, battery systems, and potentially long-duration storage solutions such as hydrogen. Notice the conditional language. Hydrogen does not automatically become the answer. Its relevance increases where three conditions converge: high renewable penetration, constrained transmission expansion, and strong demand for firm, clean power. In such environments, the value of stored energy during peak stress rises. If electricity prices spike during constrained periods, the economic spread between low-cost production hours and high-value discharge hours can widen. That arbitrage potential improves hydrogen's financial case, though it does not guarantee profitability. Now we apply the competitive edge lens. If subsidies decline, capital costs remain elevated, and utilization is lower than projected, which hydrogen projects survive? The answer is not generic hydrogen production. It is hydrogen with demand certainty. A project co-located with a large industrial or digital load and backed by long-term offtake agreements carries less revenue risk than a merchant facility hoping future markets develop. Under AI-driven energy strain, hydrogen tied directly to critical infrastructure may possess stronger demand lock-in. But we must also acknowledge operational complexity. Hydrogen systems involve electrolyzers, compression, storage, safety protocols, and reconversion equipment. Data center operators prioritize reliability and simplicity. Therefore, early hydrogen integration is more likely to appear in hybrid systems rather than standalone power architectures. For example, a grid-connected data center may incorporate hydrogen-capable turbines as a secondary or tertiary backup layer, gradually increasing hydrogen's share as supply chains mature. Temporal analysis matters as well. In 2030, hydrogen may still face cost challenges in many markets. Electrolyzer capital expenditures remain significant. Utilization rates influence levelized cost heavily. If electrolyzers run only during surplus renewable hours, low capacity factors can drive up cost per kilogram. However, by 2035, if renewable overbuild increases and curtailment rises, more low-cost electricity windows may become available. In that context, hydrogen production economics improve. By 2050, in a deeply electrified, high-renewable system with heavy digital infrastructure load, long-duration storage becomes less of a niche tool and more of a structural component. Capital markets play a role here. AI infrastructure attracts substantial investment. If investors perceive that energy constraints threaten digital growth, capital will search for solutions that unlock scalability. Hydrogen projects directly linked to relieving grid strain in high-growth regions may attract different investor profiles than those framed purely as decarbonization plays. Again, this is conditional. The linkage must be credible and contractual, not theoretical. There are counter-arguments worth taking seriously. Gas-fired generation remains cheaper and simpler in many markets today. Some AI operators may prioritize speed over carbon intensity. Nuclear capacity expansions could provide firm power in specific regions. Advanced geothermal could emerge as a scalable solution. Long-duration battery technologies may mature faster than expected. If these alternatives scale efficiently, hydrogen's role could narrow. But energy transitions rarely depend on a single technology. They evolve through layered solutions responding to different constraints. Hydrogen's comparative advantage lies in large-scale, long-duration storage and sector coupling. It is not the most efficient tool in unconstrained systems. It becomes more relevant when flexibility and duration are scarce. Let us stress test the thesis. If AI demand growth slows, grid expansion accelerates, and firm clean power from nuclear or geothermal scales rapidly, hydrogen's urgency declines. If electrolyzer costs stagnate and renewable electricity prices rise, hydrogen economics worsen. If data centers accept higher carbon intensity temporarily, hydrogen deployment slows. These are valid invalidation scenarios. That is why hydrogen should not be framed as inevitable, but as conditionally strategic. From a systems perspective, AI expansion shifts electricity from background infrastructure to a central economic driver. When electricity becomes the bottleneck, technologies that enhance flexibility gain importance. Hydrogen's role is not to replace direct electrification, but to complement it in high-strain nodes. It functions as a buffer, converting surplus energy into stored chemical form and releasing it during stress periods. For industrial developers and energy planners, the critical exercise is scenario modeling. How does hydrogen project viability change under different electricity price curves? What happens if carbon pricing rises significantly? How do financing costs impact long-duration storage competitiveness? Where do utilization rates cross viability thresholds? These questions require structured analysis rather than narrative enthusiasm. This is exactly why systems-level hydrogen evaluation matters. Understanding capital structure, capacity factors, policy volatility, and demand contracts determines whether hydrogen projects survive beyond announcement stage. Platforms dedicated to industrial hydrogen analysis exist to provide that clarity. For those evaluating hydrogen within AI-stressed energy systems, structured economic modeling and survivability testing are essential tools rather than optional extras. Stepping back, the broader pattern is consistent with historical energy shifts. When new economic drivers emerge, they stress existing infrastructure. Railroads stressed steel supply. Electrification stressed coal and oil logistics. Digitalization is now stressing electricity systems. Solutions that appear inefficient in calm conditions may prove valuable under strain. Hydrogen sits in that category. Not optimal everywhere, but potentially indispensable in specific contexts. The responsible conclusion is not that hydrogen will power AI. It is that AI-driven electricity growth increases the strategic relevance of long-duration flexibility solutions. Hydrogen is one of them. Its success depends on cost discipline, utilization optimization, contractual demand alignment, and integration simplicity. Under the right conditions, it could act as a pressure valve within constrained grids. Under the wrong conditions, it remains expensive and underutilized. So the real question is not whether hydrogen wins. It is whether electricity systems under AI expansion create enough stress to reprice resilience. If they do, hydrogen's role expands. If they do not, hydrogen remains selective and targeted. Either way, hydrogen's future will be shaped less by ideology and more by system strain. That is the lens through which this conversation must be viewed. Not hype, not dismissal, but stress-tested economics within evolving energy systems.